Okay, so we have our equation here, our two equations. Okay, so we have the definition of f hat and then how we get effective number of codons. I think this is the easiest way to look at it. We calculate f hat for each amino acid, and then we sum it over amino acids. So f hat is the probability, well, f hat is roughly the probability that if we pick two codons encoding the same amino acid in our gene sequence, that they'll be the same. It's easiest to see this when we do f hat is around just pi squared summed. So if we have two equally frequent codons in a two-box codon, then this would be equal to the sum of 1/2 squared plus 1/2 squared, which is equal to 1/2, which makes sense. Given that we've picked one codon, the chance that the other one is the same is just 1/2. If instead it was 3/4 and 1/4, then this would be 3/4 squared plus 1/4 squared, which is 5/8. So this is the more skewed it is, the higher this number is going to go. If it's 100% and 0, then we get 1. Okay, so this is the probability that if we pick two codons, they're the same, which is sort of like the same thing we do when we're talking about effective population size. Effective population size is given two alleles in the population, what's the chance that they had the same ancestor in the previous generation? Or at least that's one definition for it. So what's the chance that these two have the same common ancestor? Well, that's just 1 over n if everybody has the same fitness. But if one of these individuals has much greater fitness, now it's going to be the probability is going to be greater than 1 over n, and so the inverse of that will be less than 1 over n. That is, in a randomly mating population with no selection, we get f hat is equal to 1 over n. So ne is equal to 1 over f hat, which is equal to n. If instead there's difference in fitness, then we get f hat is less than 1 over n. So f hat is greater than 1 over n, the chance that two individuals have the same common ancestor. Therefore, ne is less than, well, ne is equal to 1 over f hat, which is less than n. Right, so this result where ne is often smaller than n. Okay, so getting back to here, then we just do this for each codon. We basically do effective population size or effective codon number per codon, and then we sum over them. So then this is generally what's going on here. I said this f hat is sort of like this f hat. So notice that when n gets very large, so we can rewrite this as just dividing everything through by n. So notice when n gets very large that this term goes away. This goes to 0, and this term goes away. And then we're just left with this, which is our intuitive sense that we change, that we pick the two, the probability that we pick, that the two codons we pick are the same. So then this stuff is just correcting for small sample size. And so a weird thing can happen here, like let's say we pick 5 A ending codons and 5 G ending codons. Well, then this would be 1/2 squared times 1/2 squared, plus 1/2 squared. So this would be 0.5. N is 10 minus 1. So the top is 4, and then the bottom is 9. So we get 4 over 9. When we flip that over, we get 2.25 codons. So the contribution here would be larger than the actual number of codons, which is surprising to me. But that's what happens when things are more even than we'd expect at random. Anyway, there's a try.